Okay, everyone. Good afternoon. Welcome to the colloquium of this week. And this week, we're very happy to have Nathan Seiberg visiting us from IES. I don't think that he needs much introduction, but just to show that I'm doing my job properly, here it goes. So Natty is a theoretical physicist, and he has made fundamental contribution, a range of fundamental contribution to string theory, to particle physics, and to quantum field theory in general. So among some of his more prominent contributions, or actually the ones that I can better understand, here's a list. He laid down the mathematical foundation of rational two-dimensional conformal field theories. He studied string theory with non-commutative geometry, and he proposed electromagnetic duality in Yang-Mills theory, which has now been generalized to a web of duality. And he found exact solutions to supersymmetric gauge theories, and the list goes on. So Natty has won many awards for his outstanding contribution. And among all these awards, here are just some of the more shiny ones. In 1996, he was named a MacArthur Fellowship, which is also known as the Genius Grant. And in 1998, he was awarded the Heinemann Prize for Mathematical Physics. In 2012, he was awarded the Fundamental Physics Prize, and then in 2016, the Dirac Medal. The reason we have Natty here today is actually on something related to what I was interested in and I have been working on. And I'm not a string theorist or a high energy theorist. I study condensed matter. And it turns out that we have been interested in a same set of models, which are called fractal models. And I first learned about them as a quantum information student. And over the years, developed a strong interest in the topic. And it's very exciting to see that people like Natty, coming from a field theory perspective, also taking an interest in the topic. And I think that's what he's going to tell us today about how to extend quantum field theory based on these the very exotic properties found in these models. So so before I let Natty take away, I want to say that if you have a question, you can type it in the Q&A section, and if I might ask you to unmute yourself during the process of the talk, or maybe leave the question until the end of the session. All right, so without further ado, Natty, please go ahead.
Okay, can you hear me?
Yes.
Good. So first of all, thank you very much here for the invitation to come and give this talk and for the generous introduction. I'm actually quite embarrassed to give this talk because I feel like carrying coal to Newcastle. This is particularly relevant in the case of shear because about 2 years ago, Princeton University hosted a conference about fractals. And as part of the conference, Shia gave a very, very inspiring colloquium. And after that colloquium, I decided that I should stop whatever I'm doing and I should think about fractals. It was really fantastic. So that's what I'm going to talk to you about today. Now, the talk will have two parts. In the first part, I'll talk about quantum field theory in general. And in the second part, I'll talk about beyond how we might need to go beyond the standard framework of quantum field theory. Now, I understand that the audience here is quite diverse. I actually can't see you, so I can't see how many there are or what your background is. So I'm going to start at a very low level and gradually go up. And again, since the audience is very diverse, I thought that in order to put things in context, I should start with a very, very broad brush map of physics to see how various ideas are connected. So I'm going to start with classical physics. This is really ancient stuff. And it's divided to two parts. There's classical mechanics describing the time evolution of a finite number of particles. And the names associated with that are Newton and Lagrange and many followers. And the mathematical setting for that is the topic of ordinary differential equations. In fact, the whole idea of differential equations and calculus more generally was partly motivated in order by the desire to understand the time evolution of a finite number of particles. Moving quickly through the centuries, we move to classical field theory. So unlike classical mechanics, here the number of particles or the number of degrees of freedom goes to infinity. In fact, it's a continuum of degrees of freedom. So we have a continuum of degrees of freedom and they all evolve in time. And our goal is to understand how they evolve in time. And examples are the electromagnetic field, that's in electromagnetism or in Maxwell's theory, this is Maxwell, or the velocity of a fluid. This is described by the Navier-Stokes equations from 1822. And it could be the metric in the context of general relativity, and I put a photo of Einstein. And again, there's a very natural mathematical setting for them, and the topic is PDEs, or partial differential equations. So both classical mechanics and classical field theory are described by calculus, and we can think of calculus as being the language of classical mechanics. So what are the characteristics of calculus? So it's again Newton here. It was new mathematics at the time. It was invented by Newton and by Leibniz. It was partly motivated by physics. There were also other motivations. And it has had many applications in mathematics and physics. And over the years, it had applications also in other sciences, in engineering, and even in the social sciences. This is the sign of a deep idea. Calculus is a deep idea. And the test of a good idea, or in a deep idea, is that it has many applications far beyond what it was originally designed to do. It was designed to do one problem, to solve one problem, or to address one problem, but it has lots and lots of other applications. I think that calculus is also clearly a mature field, and I'm going to propose the maturity test for a field. A field of knowledge is mature when it's fully streamlined. And the way to test it is to look at various books and how courses are being taught. And if you look at various books or different universities, how calculus is being taught, it's more or less the same order. It's go more or less in the same sequence of events, the same sequence of topics. And for me, this is a sign that the field is mature. Moving to the 20th century, we have quantum physics. And again, it's divided to two parts. First is quantum mechanics, which is the generalization of the classical mechanics. And it describes, again, the time evolution of a finite number of quantum particles, not classical particles and quantum particles. Here, I put a photo of some of the people who contributed to quantum mechanics. It's really a much larger set of people. And again, just as we had ODEs and PDEs in the previous entry, as entries in the previous page, here, the natural mathematical setting is the topic of operators in a Hilbert space or a functional integral for quantum mechanics. This is more or less understood. It has been tested experimentally, and theoretically it's in a very, very firm ground. And this is, again, a mature field. And as we have moved from classical mechanics to classical field theory, we move from quantum mechanics to quantum field theory. And here we had finite number of degrees of freedom. Here we have an infinite number of degrees of freedom, and in fact, a continuum of degrees of freedom. And again, typical example is the electromagnetic field. Quantum field theory describes the fluctuations of the electromagnetic field. So we have this picture that we had classical physics was divided to two parts. Quantum physics is roughly divided to two parts. And three of the topics we discussed about so far are already mature, but quantum field theory is not yet mature. A lot is known about it, but still there's a lot of very exciting progress. It is still a very active field of research. And my own personal view is that just as we have a natural mathematical setting for the other three entries in my little map, Here, a new intellectual structure is needed in order to describe quantum field theory. And I'll say more about that soon. Now, quantum field theory is enormously successful. It exists everywhere. Let me give some examples of the branches of physics, at least, where quantum field theory exists. One place it exists is in the context of particle physics. And it's really the language to describe the standard model of particle physics. It's been enormously successful. And this is perhaps the best success of quantum field theory. It describes the electromagnetic dipole moment in enormous accuracy. This is the theoretical value as of today, and this is the experimental value as of today. Lots of significant digits, and every digit here tests our understanding of quantum field theory at more and more detail, and tests our understanding of how the structure, how the theory works, and what its elements are with enormous accuracy. And no other branch of physics comes even close. So two lessons from that. One is that we really know what we are doing. This is not a random success. We really know what we are doing when we compute it. And the second lesson is that the experimentalists have one more digits that we, the theorists, don't yet have. So they're ahead of us, and we must work harder. The second place where quantum field theory appears is in the condensed matter physics. And here, in fact, many of the ideas in quantum field theory originated from condensed matter physics. Others originated from particle physics, and influence from one field to another have been many very, very successful over the years, and I can give specific examples where there was such cross-fertilization. And the way it appears in condensed matter physics is to describe the long-distance properties of material. We have different materials, and at short distances, they have some lattice and some atoms, and they interact with one another. At long distances, they exhibit phases and phase transitions between them. And continuum quantum field theory describes the phases and the transition between them. I'll say a lot more about that in the coming slides. The next application is in cosmology, especially in the early universe and the description of inflation, which uses quantum field theory rather heavily. In string theory, quantum field theory also appears, and it appears in three different places, which are really logically quite distinct. First, the string is a one-dimensional object, and as it evolves in time, it sweeps a two-dimensional world sheet. And as it does that, we have a two-dimensional field theory, one space, because the string is one-dimensional at one time, and we have a 1 + 1 dimensional field theory living on the world sheet of the string. The second application is totally distinct, and that's in the low energy approximation of string theory. When we examine how the strings behave at very low energies, gravity is negligible at low energies, and what remains are non-gravitational interactions, and string theory becomes effectively a quantum field theory at long distances. This is one of the successes of one of the reasons we are excited about string theory, because at long distances, it connects to the same language and the same ideas we would like to have anyway at long distances. And most dramatically, in some contexts, especially in the topic of gate gravity duality, quantum field theory gives us a whole description of the whole theory, not just the low energy approximation, but of the whole theory. So these are three distinct applications of quantum field theory in the context of string theory. In addition to applications in physics, quantum field theory has had a lot of applications in mathematics, especially in geometry and topology, where it had profound implication, profound impact on these other fields. So this sounds a little bit similar to what I said earlier about calculus. So let me repeat this calculus slide I had earlier and compare quantum field theory to calculus. And the point I'm going to advance is that quantum field theory is the modern calculus. And just as calculus still is the language of classical physics, quantum field theory, which generalizes it, I would like to describe it as, or think about it as, the language of physics. So this slide mirrors the slides I had about calculus early on. It's a new mathematics. Calculus was a new mathematics. Quantum field theory is a new mathematics. In fact, it's not yet even mathematically rigorous. And we would not like to have a rigorous structure for the sake of rigor. We as physicists do not care very much if it's mathematically rigorous or not. But I think that the fact that it's not yet rigorous tells us that It's not just that we cannot satisfy the mathematicians with the rigor, we do not yet fully understand what we are doing if we cannot state it in a mathematically rigorous way. The second entry in the calculus slide was that it was motivated by physics. This is again very similar. This was clearly motivated by physics. And it has many applications in mathematics and physics. Very much like calculus, quantum field theories had many applications in mathematics and physics, applications far beyond what it was originally designed to do. It was designed to do originally the interactions of electrons and photons, or some phase transitions in condensed matter physics. And as we saw, it describes string theory and even applications in mathematics. So this is clearly a sign that quantum field theory is a deep idea. So far things look very similar to calculus, except that quantum field theory fails the maturity test. If you look at quantum field theory courses at different universities, or if you look at quantum field theory books, you will see that every one of them is different. They start from a different perspective, the order of the presentation is different, and so forth. This is another sign that the field is not yet mature, and for researchers it's a good thing because it means that we have something very exciting to work on. We have open problems, we need to understand them better. All these are indications that we are still missing big things. There are still many things that we should understand, and we don't yet understand them. Let me touch on some aspects of quantum field theory in a little bit more detail, and then we'll go back to the big things that I think we're missing. And the topic I'd like to talk about is separation of scales. In physics, we often have a different effective description at different length scales. In fact, this is true not only in physics, as I will soon demonstrate, this is true in almost every branch of science. We have effective descriptions at different length scales. This is quite significant because it gives us a simplification. We don't need to understand all the physics at all length scales in order to understand what happens at a particular scale. We can study the hydrogen atom without understanding all the details of the Higgs boson. And similarly, we can describe the flow of water without understanding all the underlying molecules underneath. Also, as we explore nature in more and more detail, and we kind of peel the onion one layer at a time, we gradually uncover a deeper truth. This is known in philosophy as reductionism. We always go to find a more complete theory, a deeper structure of nature at shorter distances, and then we can ignore what happens at shorter distances and find an effective theory. This is the simplification, and then we can proceed and find a deeper truth. Now, here are some examples of it. In thermodynamics, mankind understood thermodynamics before they understood statistical mechanics, and before it was understood that there are molecules bouncing around. Similarly, I mentioned the Navier-Stokes equations earlier. They describe hydrodynamics, the flow of fluids. And later it was understood that what's really going on there is that we have molecules bouncing around, and instead the effective description at long distances involves some PDE that describes the motion of the fluid. Some of us, for obvious reasons and unfortunate reasons, became interested in epidemiology during the last year. And again, we can see here this hierarchical structure of separation of scales. We can be interested in the shortest distances in how the viruses act, how the viruses mutate, and so forth. And then at a longer scale, we can ask, how do we treat the individual patients, how we make them feel better, and how we reduce the spread of the disease. And at even longer distances, we don't have to pay attention to all the details of the virus. We can look at the statistics of how the pandemic evolves, how many people are sick, what the mortality rate is, etc. And at every scale, we have an effective theory at that scale, and we don't need to understand all the details of what happens at shorter scales and longer scales. So this philosophical structure, which exists in all of science, is really very significant in the context of field theory. And this is the notion of effective field theory and the renormalization group. So I mentioned two people, who really contributed a lot to it. These are Wilson and Weinberg. And they said that there are different field theories describe phenomena at different length scales or at different energy scales. So we can focus on long distances and find an effective field theory at long distances. And there might be a different field theory acting at shorter distances. So we can have different theories at long and short distances. We can think of it as follows. At short distances, we have what we call the UV theory. UV for short distance or ultraviolet. It describes what happens at short distances. If you wish, this is where we formulate the problem. In the context of condensed matter physics, we take some atoms, we throw them in a box, we shake it, and the atoms do something. And our goal, this is the problem, is to figure out what the atoms will do. What are we going to find at long distances? At long distances, we have the IR, or the infrared theory, which describes what's going on at long distances. And the theory at long distances describes the possible phases of the system. So if you wish, this is the problem, and this is the answer. We have two different descriptions. The description of what happens at short distances. This is given to us. And at long distances, we find the phase of the system. This is the answer we would like to find. And there are some interesting and important properties here. The infrared theory, the long distance theory, is independent of most of the UV details. I demonstrated it earlier in the case of hydrodynamics when I said we can describe the flow of the fluid without keeping track of all the molecules and how they interact with each other. I gave another example with the epidemiology of how the pandemic evolves, and we don't need to understand all the details of the virus in order to describe that. Related to that, even if we have at short distances a lattice, at long distances it becomes like a continuum. If we look at a chunk of material, it has atoms at short distances, but when we look at it at long distances, it looks perfectly smooth. Space becomes smooth. In the context of calculus, this is the idea that if we start with a sum, and the object that we sum are near each other, we can approximate the sum by an integral. In a similar way, we can approximate the lattice by a continuum field theory. The next topic I'd like to touch on is the phases of quantum field theory. So we consider the system in a large but finite volume. And then we have a Hamiltonian. We need to diagonalize the Hamiltonian. And very roughly, the spectrum of the Hamiltonian can be one of two ways. Option one, it is gapped. There is one or some number of ground states at zero. Then there is a gap, and then there is a continuum of states. An example would be a free massive particle. So the ground state has no particles at all. And then we can have one particle that has energy. Energy is the same as its mass. This is this distance here. And then the particle can have higher and higher energy as it has more and more momentum, and it populates all these continuum of states. And there is further refinement depending on whether we have only one ground state here or several ground states. And that's known as topological field theory. The second possibility is that the spectrum is gapless. So this gap closes, and we have a ground state, or perhaps several ground states, and then immediately we have a continuum. This example of that is that when we have photons, the photons are massless, so we can have states with arbitrarily low energy. By giving the photon smaller and smaller momentum, it has smaller and smaller energy. And again, we have further refinement here. The photons are free at long distances, but if they interact with each other, then we have what we call the conformal field theory, and the notion of particle is ill-defined, and it's a little bit more complicated. And this is really very rough description of the classification, and there's a more refined classification depending on more details that I'm not going to talk about. So this ends the first part of the talk where I talked about quantum field theory, and now I advance the point that this is the language of physics. It describes everything. Everything is wonderful. So from this point on, things start becoming a little bit more strange. The first thing I would like to stress is that there are strong indications that traditional quantum field theory needs an extension. It does not describe all the systems that we know. It describes most of them, but not all of them. And the first indication of that came actually from string theory. String theory is a theory of gravity, and it includes both gravity and other interactions. and it has a parameter which we can call Newton constant. We can try and find example where we can gradually turn off Newton constant. If we turn off Newton constant, the gravitational interactions become negligible. We are left with, if we turn it off completely, we are left with a system without gravity. A system without gravity is typically a quantum field theory. I said that earlier, that if we turn off gravity, string theory becomes quantum field theory. That's the simple case. But in certain examples, certain space-time backgrounds, the low energy theory is clearly not a local quantum field theory. It's not a standard quantum field theory. And two examples are quite prominent. The first is field theory in a non-commutative space, and the second is known as little string theory. I'm not going to elaborate on them, except to say that they are consistent because they are a limit of a consistent theory. They do not have gravity. They look somewhat similar to quantum field theory, but they are obviously not quantum field theory. They do not satisfy the axioms of quantum field theory. And there might be other examples. So these are examples that we just bumped on. Other examples came from certain lattice models. I said earlier that if we start at short distances with a lattice, at long distances, the lattice looks continuum, like a continuum, and the continuum at long distances is described by a continuum quantum field theory. But in certain example cases that I will soon elaborate on, that's not the case. In the case of fractal models, the low energy theory is not described by a standard quantum field theory. So the examples are quite different, and I mentioned three specific examples: little string theory, field theory in a non-commutative space, and theories of fractons. They came from different places, and in all cases, we take something that we think we understand. It should be completely standard, but in fact, it's not. These examples are quite different, and they appear from different places, but they have some things in common. They have some common features. First of all these examples are not Lorentz invariant. In fact, some of them are not even invariant under spatial rotations. This is true for the string theory examples, and also true for the lattice examples. Perhaps that's not very shocking. We can have field theories which are not Lorentz invariant, and we can have field theories which are not rotationally invariant. So that by itself is not surprising. And that, if that had been the case, there would be no reason to talk about it. But what's more shocking is that they have something which we can call UVIR mixing. I emphasized earlier the significance of separation of scales. This is very significant in all of science, especially in physics, and even more so in the context of quantum field theory, in the use of the renormalization group. In all these examples that I mentioned, the long distance or low energy phenomena reflect high energy physics. This clear separation of high energy and low energy does not exist in the three examples. So they really violate the law, and that's very significant. And I'll say more about that soon. In addition to these common features, there are also bizarre properties which are quite different in the different examples. And for all we know, there could be other examples, either other examples from string theory or other examples coming from lattice models, which exhibit even more peculiar features. So in the next part of the talk, I will focus on one of these, and I'll talk about fractons. And in the coming slides, I'll give a lightning review of fractons. And this is not my work. In fact, nothing until this point was my work. And I'll talk a little bit about fractals, and then I'll go to more modern ideas. So first, a brief history of fractal models. And the early models of fractons were motivated by totally different considerations than the ones we'll focus on here. The first paper is by Shamon from 2004, and the second paper is from Ha 7 years later. Notice the time difference between the two papers. I also decided to spell out the titles of these papers. These are Quantum Glassiness in Strongly Correlated Clean Systems, an example of topological overprotection. And the second is Local Stabilizer Code in 3 dimensions without string logical operators. The titles show that these papers were not motivated by physics. They were motivated by quantum information. They were motivated by computer science. no phases of matter, nothing about the fact that it violates quantum field theory. That wasn't there. That was in 2004 and in 2011. It took until 2015 or 16 to realize that these models also have totally different application and totally different surprise. And so the realization of the significance of these models as phases of matter came in these two papers. And again, I decided to quote the titles: A New Kind of Topological Quantum Order, a dimensional hierarchy of quasi-particles built from stationary excitations, and Fractal Topological Order, generalized lattice gauge theory, and duality. This starts sounding more like physics than quantum information theory. So, and it took indeed several years to realize the shift. This is not to say that these models are not interesting for quantum information or not interesting for computer science. It's just to say that there are also other interests in the same models. And after these papers, where it started looking more like physics, there started a flood of papers, and I mentioned some examples of them. First of all, there were more examples. All these papers are gapped, or called the classification gap phases and gapless phases. Pretko described the gapless models, so I'll soon mention that in more detail, associated with the strange gauge theory, which had been suggested 10 years earlier by Shu. And there were many other constructions of more examples, couple layer constructions, etc., etc. I'm not going to talk about that. And gradually, more connections to other fields appeared, including elasticity, quantum information, that in fact, this is where it started, and connection to quantum field theory. So this is a huge field, and I'm actually not an expert in the field. As I said, I'm a newcomer to this field, so I clearly cannot do justice to it here, but I'll mention some examples in the coming slides. So the first example I want to talk about is the model known as the X-cube model. And it is associated with Z2 spins. So this what today is called the qubit. When I learned physics, this was called the two-level system. And we can call it also a Z2 spin on every spatial link. So we have a lattice, and on the lattice, on every link, we put a variable, a Z2 two-level system, or a qubit. And the Hamiltonian is a sum of terms. There are two kinds of terms in the Hamiltonian. The details are not important. They're very important in order to get the physics straight, but for the purpose of this talk, the details are not important. The sum over the cubes, and for every cube, we multiply sigma 1, the Pauli matrix, around the cube, for all the links around the cube. And then there are other terms associated with the sites, 3 terms for each site, site S. We multiply sigma 3 of all the 4 links touching the site here in the XY plane, in the YZ plane, or in the XZ plane. And we sum this up, and this is the Hamiltonian. The main point I want to stress about this Hamiltonian is that it is innocent looking. It looks completely standard. It's not quite the Ising model, which is the canonical example of a system of Z2 spins. It's a little bit more elaborate, but it's not that much more elaborate. There are only Z2 spins, and the interactions are local. Every spin talks only to a finite number of neighbors, so it's not that different. Yet, the outcome of this model is completely different than any of the other models constructed out of spins. And here are some of the peculiarities of this model. If we start with a lattice with Lx times Ly times Lz sites with periodic boundary conditions, there is a huge ground state degeneracy. This is the number of ground states. This formula is shocking. It's shocking for several different reasons. First of all, it depends on the number of lattice sites. Normally, the number of ground states of the system does not depend on the number of sites. So that if we just add another layer of atoms, so we make Lx bigger by 1, the number of ground state is multiplied by 4. So this is huge. Second, we know examples where the number of ground states grows with the number of sites, but then it grows with the volume. This grows with the length. It is subextensive. The next thing which is surprising about that is that if we just take this formula and we try to take the continuum limit, what's the continuum limit? We say there's a lattice facing little a, we take it to 0, We take the number of sites to infinity with fixed physical length. As we do that, this formula diverges. So this system has an infinite number of ground states in the continuum limit. And this is not the kind of infinity that field theory often has, and we know how to get rid of using the process of renormalization. This infinity is really there because we compute the physical observable. And the physical observable is the number of ground states, and it's infinite. I would like to present that from a slightly different perspective. The ground states reflect short distance physics. If we have separation of scales, we can have an effective theory at low energy, which captures the long distance physics, and it's independent of most of the details that happen at short distances. Here, the number of ground states grows with the number of sites. So that means that the long distance, low momentum physics, long distance physics depends on short distance physics. It depends on high momentum modes. It depends on modes which change from one lattice site to the next one. This is very, very surprising because it violates these general principles of physics that I mentioned earlier. A few more facts about this model. The spectrum is gapped. I said that already before. And the model is also stable or robust. If we take the Hamiltonian that I wrote earlier and we deform it a little bit by adding some other terms to it, as long as the deformations are small enough, the low energy physics doesn't change. So this model is stable, and it also has very peculiar excitations. There are localized excitations with restricted mobility. There are particle-like excitations, which are kind of energy localized in a certain region that cannot possibly move. It could split to other excitations, but by itself, it cannot move. There are also excitations that are restricted to move on a line, X, Y, or Z, but not diagonally. They cannot move on a diagonal. And in fact, specific particles can move along the X directions and other ones along the Y direction around Z. And there are particles that can move on a plane. This is all very peculiar and unlike other models that we know about. Let me mention the other model, which has actually appeared earlier. This is Haas code. Now there are 2 qubits at every site. And again, the Hamiltonian has 2 terms. The details are not important. So for example, here sigma 1 acts on the first spin and 1 acts on the second spin. So we multiply all these in this cube plus all these on this cube, and we sum over all the cubes. And again, this is an innocent looking Hamiltonian. It's a little bit more complicated than the previous one, but it doesn't look that bad. Every spin interacts only with nearby spins with a finite number of them. It looks like the interaction is local, and yet it has many bizarre properties. In particular here, the ground state degeneracy is a more complicated function of the 3 lengths. It's not linear in the length, but it's some function of the lengths. And it's a very complicated function. Even when all the lengths are equal, this function is complicated. And in fact, it's not even monotonic. We add one more layer to the lattice. We add one more layer of atoms to the lattice. And the number of ground states can drop to be very small, or it can jump again and become very large. It's not even monotonic in L, but it is bounded in L. So if before this thing in the exponent was divergent and it was already puzzling enough, here it's not even linear in L, and therefore there isn't a well-defined limit. So in this case, the number of ground states in the limit of L going to infinity is ambiguous. And it indeed begs the question, is there a continuum limit at all? Because before the continuum limit looked subtle, because the number of ground state diverges, here there isn't even a well-defined limit. So is there a continuum limit? This brings me to the last set of models I would like to describe, and they came from Fractal. And he was motivated by earlier models of symmetric tensor gauge theories in the continuum and on the lattice due to Schroop. In ordinary electrodynamics, we have a scalar potential, A0, and it undergoes gauge transformations with the time derivative of the gauge parameter. And there are spatial components, the vector potential. Here, should replace it by a tensor. So ij are 2 spatial indices, and this is a symmetric tensor. And other gauge transformations that transform with a double derivative. then it's straightforward to check that there are gauge invariant electric and magnetic fields. Normally, E is a vector and B is a vector. More precisely, it's a pseudo vector. In this example, both of them are various tensors with some indices. Again, the details are not important. The important thing here is this is some kind of a generalization of Maxwell's theory with a little bit more indices. And just as Maxwell's theory has massless or gapless excitations like a photon, I mentioned that earlier, this theory also has some kind of a photon-like excitation. And I will say more about that soon. If these are the gauge transformations, we have Gauss law. And Gauss law, following the same spirit as in Maxwell's equations, are a second derivative of the electric field, and that's the charge density. And from here we learn that the total charge is conserved, but also the dipole charge is conserved. Because if we substitute, what do? We substitute the left-hand side of this equation here, and then we can integrate by parts and we get 0. And even if we have one x here, we substitute it, one derivative kills x and the other derivative gives us 0. So this means that this is also a conserved charge. So in this system, both the total charge is conserved and the total dipole charge is conserved. This means that particles have restricted mobility. Because if we have some particle and it has charge, if only charge is conserved, the particle can move to another point and preserve charge. But here also the dipole charge is conserved, and therefore a particle cannot move. This whole set of models raise many, many interesting questions. First of all, are there more examples with perhaps more exotic phenomena? And there are other examples, and they're kind of similar. Second, what is the underlying reason for this bizarre behavior? Why did it happen? Why do we have these strange properties? And we would like to have some kind of a way to organize all possible phases and all possible theories. Because the examples so far are examples that people bumped on. They accidentally discovered them. And there isn't a clear classification or a clear organization. Every time there's a new example, we add another item to the classification. That's not the way to do it. And in ordinary phases, when we discuss ordinary phases of matter, the organization is based on continuum quantum field theory. I've said that before, and it's still true. Is there a sensible continuum quantum field theory to give us the organization of these theories? Is there a sensible continuum field theories for that? And I've already pointed out some of the challenges in doing that. And there are, of course, many more. So we're going to look for a low energy continuum quantum field theory. Is there a low energy continuum quantum field theory for this? So the properties of fractons, and in particular this UVIR mixing that I mentioned, makes it very challenging to find such a continuum field theory because they seem to contradict the renormalization group picture. Phenomena at long distances, like the number of ground states, are very sensitive to short distance physics, like the number of layers. So what we're going to do is try to slightly extend the framework of continuum quantum field theory in order to accommodate fractons and other models. Now, we should tread very, very carefully here. Quantum field theory is a very delicate structure. It's actually quite miraculous that it makes sense. In fact, I said earlier that it's not even mathematically rigorous. And if we start messing with it, we might lose the whole structure. So we should extend the framework. If we try to extend the framework of quantum field theory, we should be extremely careful and try not to ruin it completely. And that has two motivations. First, as I said before, it will give us a universal description of these systems. Universal in the sense that it is independent of most of the details of the microscopic model, and will also give us, related to that, some way to organize the models and to classify them. And in the other direction, if we need to extend the framework of quantum field theory, this could teach us how to extend it. And I said earlier, there are also other motivations why we might need to extend quantum field theory, other examples that I mentioned. So I was fortunate to have a fantastic collaborator, Shuheng Shao. And together we put forward some exotic continuum quantum field theories, which have some new elements. So these are the elements. First of all, space-time symmetries. That's not shocking. said before, in addition to translations, we have no Lorentz invariance, and we do not even have rotation symmetry. We only have discrete rotations. In the case of the X-cube model, we have only 90-degree rotation. In the case of Haas code, we have only threefold rotation. And we impose various global symmetries, exotic global symmetries, non-standard ones, and we gauge them. Again, this is not new and not surprising. The main new element that we injected is that we were willing to tolerate discontinuous fields and gauge parameters. Now, on the lattice, everything is discontinuous because the degree of freedom or the field at every point on the lattice has independent values, and there is no notion of continuity. In the continuum, on the other hand, everything is smooth. When we have differential equations, say for Navier-Stokes equations, it's very similar. At short distances, we have molecules, nothing is smooth, but we describe the flow using PDEs that describe smooth flow. So we are going to be in between. We are going to have certain discontinuities, not as discontinuous as on the lattice, but not as smooth as as in the continuum. So the first example that we'll discuss would be a tensor gauge theory to demonstrate how it works. So we're going to discuss a variant of the tensor gauge theory I discussed earlier with indices I and j by excluding the term with I equals j. This was first proposed by Xu and Wu, and it was named by Ma, Hemley, and Chen as a hollow tensor gauge theory. It's hollow because this is a symmetric tensor, and if I is not equal to j, this is a symmetric matrix. We remove the diagonal of that matrix, so we have fewer degrees of freedom. And the gauge symmetries are the same as what I had before, except that now, since I is not equal to j, it's not invariant under SO3 of rotations, but only under the cubic group rotations. So we proceed as before. We have electric and magnetic fields. They're gauge invariant. And now we're going to work out the spectrum of this theory. So this is straightforward. We take a plane wave solution, we substitute it in, and this is the dispersion relation of the system. And this formula includes higher derivatives. That's because the electric field and the electric field has higher derivatives, and therefore we have more powers of momenta here. And the main thing that I would like to emphasize here is if we substitute Kex equals Ky equals 0, so you see this is 0, and this is 0, this remains. This is 0, this is 0, this is 0, and therefore omega equals 0 is a solution. So with this dispersion relation, we have zero frequency or zero energy modes with arbitrarily large Kz. This is the UVIR mixing. So the UVIR mixing comes about because we have modes of this quote-unquote photon, of this particle of the system. There are modes which have zero frequency and arbitrarily large momentum. We can be at very low energies, and we are still sensitive to things that happen at very high momentum and correspondingly at very short distances. So this is the key to the peculiarities of these systems. In fact, it means that we have an infinite number of zero energy states, because for every value of Kz, we get a zero energy state, provided Kx and Ky are 0. And we have the same thing in the other directions. The presentation here is a little bit too quick, because one has to analyze the quantum effects more carefully. But in this particular system, this remains true in the quantum theory. How do we think of such a gauge theory? We have to think about gauge transformations. So the gauge group is U1, which means that the gauge parameter alpha is identified with alpha plus 2 pi. This is the same as in ordinary gauge theories. And usually alpha is a continuous function. This gauge functions are continuous functions. But as I said, here we allow also discontinuous gauge transformation. And the typical large gauge transformation is this function. Again, don't pay attention to the details. They're not important to understand my point. But I do want to emphasize that we allow certain discontinuous functions where this theta is the Heaviside theta function. So this is a periodic function on the torus, but it can jump either in x or in y, but not in both. So there's a whole structure that goes into it, and I'm not going to elaborate about it here. But the significance of that is that with these gauge transformations used at transition functions, we find quantized fluxes. So very much in electrodynamics or in gauge theories in general, flux is quantized. We have Dirac quantization, we have Aharonov-Bohm effect, and so forth. But it comes about because of these discontinuous gauge transformations. Let's generalize it to, or not generalize, or specialize to Zn version of it. So now, instead of having a U1 theory, instead of the symmetry being U1, we rotate things by a phase. Now we have only nth root of unity as a possible phase. And the way to do that is to use the Higgs mechanism and to break the U1 gauge symmetry to Zn. So again, the details are not important. We write a Lagrangian, we write the gauge transformations. The gauge transformations of the gauge fields are as before, but we also had a scalar field that breaks the gauge symmetry. And there are also various dual descriptions of this system. So this is one of them, but there are many others, including one that was found earlier by Slagle and Kim. So again, I'm not going to go through all the details, but we can analyze this model using discontinuum field theory. Again, paying very careful attention to these discontinuous field configurations. And we find the following results. The spectrum is gapped. There's a gap in the spectrum. There's an infinite ground state degeneracy. If we regularize it using a lattice, we find this formula. There are particles with restricted mobility. Some of them can be are stuck at the point. Some of them can move along a line, and some of them can move only on a plane. Furthermore, there are no local operators that act in the space of ground states, and hence it's robust. This is the stability that I mentioned earlier. And there's also a very rich spectrum of line operators. So I'm not going to go through all the details here. This is a lot of work to get all these details straight. But the important thing is that this is a continuum field theory description of the Zn version of the X cube model. For n equals 2, this is exactly the X cube model that I mentioned earlier. So my time is already almost up, and we had a long journey starting with Newton and Maxwell and Einstein and quantum mechanics and this and that. And in the end, I've kind of took off and became more technical. So let me wrap up with a summary. So quantum field theory is everywhere. I hope I demonstrated to you that it's enormously successful and enormously powerful in particle physics, condensed matter physics, cosmology, string theory, quantum gravity, and it even has applications to mathematics. And it appears to be the language of physics. We use the same language everywhere. And there's been a lot of progress over the last several decades, but there are also big questions. So new phenomena are being discovered constantly, so it's a very exciting, lively field. But there are indications that there are big things that are still missing, and I actually find that very exciting that there are things that are missing. It's not just something that we're going to teach our students, but these are things that we can still explore and discover new things. I mentioned that certain string theory constructions and lattice models lead to peculiar systems that go outside the framework of standard quantum field theory. This is a clear indication that our understanding is incomplete and we need to extend it. I mentioned the examples of field theory in a non-commutative space, little string theory. These two examples came from string theory, and fractons that came from lattice models. Then I briefly mentioned fractons, and I talked about the fact that they exhibit very interesting and peculiar properties. The most exciting among them is the fact that we have this UVIR mixing, this mixing between short distance and long distance physics, something that is very surprising from philosophically and against the spirit of physics in the last few centuries, and seems to violate the renormalization group picture. So there's large ground state degeneracy, sometimes not even with a well-defined limit, as we take the number of sites in the system to infinity. And some observables are discontinuous. So as we move them from site to site, they have independent values. There are also excitations with restricted mobility. I do not know whether these two facts are related to each other, but these are two peculiarities of these systems. All this seems to be incompatible with this framework of continuum quantum field theory, and I emphasized that a number of times. Then we presented a non-standard continuum quantum field theory. This is an attempt to extend how we think about quantum field theory, how we think about it, to extend the kind of things that contribute in quantum field theory. I mentioned that it's invariant only under discrete rotations, and it has some exotic global and gauge symmetries. That I do not find that shocking. This point I find the most surprising one, and it is essentially inevitable. If you want to have a continuum field theory description of these systems, you must have discontinuous fields. So let me clarify the terminology. When I say continuum field theory, I mean that space is continuous. The fields that are functions of the space could be discontinuous or even singular. And we allowed certain discontinuities, such that it's more continuous on the lattice, but less continuous than in standard continuum field theories. And these continuum field theories that we presented capture all the universal properties of the lattice model. They still depend on some short distance behavior. That's because we still have some UVIR mixing, but most of the details of the underlying lattice are washed away by the time we are at long distances. This is as close to the renormalization group picture that we could hope to have here. And they also reproduce all the long distance behavior of the system, the number of ground states, and the properties of these probe particles. So this is being a long journey. Thank you for listening, and thank you, and please stay healthy.
Thank you so much. Thank you for the wonderful talk, Nadi. So now we open up for questions. So if you have questions, you can either just raise your hand or type it into the Q&A box. Either way is fine. Okay, so if you want, people are getting ready. Oh, I see some hands now. Oh, Lessig, go ahead.
Where would you put Fermi liquid or non-Fermi liquids? In some sense, information about the Fermi surface needs to be maintained, and that's a UV information.
But it's a small number of parameters. Whenever what you need to, so first of all, it's field theory. This is not outside the field theory. Sorry. And the reason is that every field theory depends on some parameters. So it's common that the long distance physics depends on some parameters. But the main point about field theory is that the long distance physics depends on a small number of parameters. In the case of Fermi liquid or Fermi surface, it's still a small number of parameters. I should emphasize that there are some similarities between physics along the Fermi surface and these systems, because they have an infinite number of conserved charges. And in some cases, indeed, I momentum in one direction mixes with properties long distances. Having said that, there's still a way to reorganize things in a way that looks more like field theory. My favorite paper on the subject is a paper by Joe Polchinski, the late Joe Polchinski, who asked himself exactly this question, and he gave the answer I just gave. There's also a paper by Shankar, I think, on the same subject.
Thank you.
Arpit, you can go ahead.
Can you hear me?
Yes.
Yeah, so I have this question. So in fracton models, we know that we get a bifurcating renormalization group, meaning that when we coarse grain and do these unitaries, we bifurcate the model. We get two different models at coarse grain length scale. So how does this come about in the field theory description, where you have the discontinuities in the fields to describe the same fracton model?
So whatever you guys do on the lattice, we can do in the continuum framework, and we can go through the details. And we don't lose any information by. So all the nice features that exist on the lattice, the continuum model reproduces them. Now, in fact, some of them are reproduced more nicely or in the continuum, as they should, because the continuum usually exhibits more symmetries, etc. So we can go through a long list. It's not something we'll be able to do at the colloquium level.
Yeah.
Definitely not in this context here, but everything can be done on the lattice or in the continuum. It's the same thing.
Okay, yeah, I was wondering if there is like a short description, but yeah, thanks for that.
So we have one question in the Q&A box, and I'll just read it. So Adrian Culver is asking, should we expect that some lattice models won't have any continuum long distance description? Analogy to calculus, a reasonably nice discrete sequence of numbers is approximately like a continuous function in some continuum limit, but presumably some sequences are not nice enough.
Well, that's clear. This clearly can happen. And there are functions that are not integrable. In the context of calculus, there are all sorts of things like that. Usually they do not arise in physics. And when we go to, so we can have functions that, say, hops around very rapidly, but usually in physics we don't have that. And there's a reason we don't have that in physics. In physics, we have this picture of the separation of scales and effective field theories, and things become smooth and so forth. So this is a counterexample. Now, it might very well be that we should abandon quantum field theory altogether, and there's no quantum field theory description of these systems. And I've been wasting my time and your time when I talked about it. The alternative is that there is such a thing, and it goes outside the framework that we know and love, and then we have to find it. I think it is a very important question whether there is such a description or not, and therefore I think it's worth trying. But there's no guarantee of success. And it could also be that some fractal models have a continuum description and some others don't. Who knows?
Who knows? Yeah.
But we'll know eventually.
Yeah, another question from Spiros, which says, what type of properties survive the UV-IR mixing and remain universal? Is there some common aspect to these properties, which the number of the ground state does not satisfy? Is there?
I presented here one example, not presented, I mentioned one example because I did not go into detail. We've actually explored a large number of systems. Some of them are equally exotic, but do not have fractals. There are other fractal models. And in every one of them, the details are different. The common thing is that you have to specify more information from the UV that you normally do in an ordinary field theory, but still much, much less than exists on the lattice. And that's what you want. You would like to have something that depends on far fewer parameters than on the lattice. But the surprise here is it depends on more parameters that you would normally have. So that's exactly what it should be like. And this is what these examples do. Now, I do not pretend to have a general theory that covers all cases. We worked out a few special examples, and for them, this is the case.
Mm-hmm. Okay. Yeah, a question from Bowen Yang. What analytic regularity conditions do you impose on the discontinuous field on continuum? By regularity, I mean along the lines of measurability or integrability.
Okay, this is a good question. I actually tried to consult with mathematicians on that, hoping that they would give me an answer. And I do not know the general answer, but on a case-by-case basis, I know how to write it. And in the example that I present of the discontinuous function that I showed here, the function could have a jumping x or a jumping y, but not a jumping both. And I could say it a little bit more precisely. So we allow so that's a way of saying it. So it's a function of two variables, which can jump in x or can jump in y, but cannot jump in both. So there's no theta of x times theta of y, but it can be theta of x plus theta of y. And this can be stated much more precisely.
We got another one. Ying Xuan Ling asking, can you imagine engineering fractal models in string theory?
I can imagine that this would be possible. In fact, some people suggested that. There are fractal models that she has suggested with others using layers. So if you replace the layer by D-brane, you have a stack of D-branes, and you couple them to each other together, you might be able to get fractals there. I do not know whether anybody actually tried to do it explicitly.
Okay. So if you have one more minute, I want to squeeze in a question. You mentioned this string theory on non-commutative geometry and the fractal model as examples beyond the usual QFT. Do you see connection between them in any way?
Okay. Personally, I don't, but I'd like to connect that to the question that was asked earlier. Forget who asked the question about the Fermi surface. So there's a recent paper by Senthil and others suggesting that non-commutative geometry could be important there. I'm not sure what to make of it, and I do not know whether it's connected, but I find it encouraging that similar issues arise in really distinct topics. And I think the way to address them is to have interdisciplinary work of people with expertise from the different topics coming together and working together.
Okay. Okay. Thank you. Thank you. This is a wonderful talk. Thank you so much for taking the time to visit us. It's great to see you, and thank you everyone for attending. Hope you have a good night.